Okay, so what I'm going to do here is run a demo with this Prosilica camera. It's running, this is a Windows machine, obviously. It's running on this Windows machine. It's an Ethernet camera, a GIGI camera, connected directly right now to the network port on this machine, but obviously it can go through switches and so on if that's your network topology. In general, it's probably a good idea with these GIGI cameras to put them into their own NIC if you have that option, because they can use a lot of network bandwidth, and if you have multiple cameras on the network at the same time, you could easily saturate GIGI. Okay, so this is the Windows command shell that the IOC is running in. So this is the Prosilica ADL screen. On the upper left on all these screens up here is information about the camera, manufacturer, model, that sort of thing. There's always a debugging button here, and if you open up the ASIN record here, this lets you turn on what's called the ASIN trace. If you don't know what that means, don't worry about it, except that if you turn on this button, you'll begin to get debugging messages in your IOC. So this is often a first step in trying to figure out what's wrong if something's not working, is to just turn on these debugging messages and display them in the IOC and capture them. Send them to the developer. We'll get to the plugins in a minute. Let's first focus on the controls for the detector itself. So here is, for detectors that support hardware binning, this is where you set the binning, the start of a region to read out, and the size of a region to read out. And then normally on a screen like this, depending on the detector, it will tell you the actual size of the image in pixels, the actual size of the image in bytes. Then there's some additional control down here for the gain, the data type, the color mode, and in this case for the Bayer conversion. And let's go through some of this and show what it means. Over on this side, we've got the exposure time and the period, the number of images to collect. So let's start. So right now I've got a 25 millisecond exposure time. I'm in what's called free run mode. So on the Prosilica, the trigger choices are free run, which basically means run as quickly as you can, collect the images as quickly as you can, determined by the exposure time and the readout speed of the camera over the GIGI. Fixed rate would have a rate that is, in addition, controlled by this acquire period. So right now, if it was free run, at 25 millisecond exposure time, it should do 40 frames a second. But when I set a 50 millisecond acquire period, that would be 20 frames a second. So it would slow it down if I went to fixed rate. And then there are actually 4 modes, sync in 1, 2, 3, 4, which are based upon a hardware trigger to the detector. Selects one of 4 hardware triggers. I don't have the hardware trigger hooked up here. Okay, so let's start the camera. So I've got an exposure time of 25 milliseconds. So in principle, you would think that should do 40 frames a second. In fact, it's doing 30 frames a second, and that's determined just by, that's what this camera can put over GIGI in monochromatic mode when you're reading out the full chip. And that works out to be something like, 40 or 50 megabytes a second. So it's using third to a half of the GIGI bandwidth in this mode. So let's go to, this is now the, well, let's look at the, what plugins are enabled. And right now, the only plugin that I have enabled is the standard arrays plugin, which is the one that's used to put the data into the EPICS waveform record, which is all we need for what I want to show right now. The other thing to be aware of for people who haven't used it is that when you first start Area Detector on a given detector and there's no AutoSave file there yet, this parameter that's called ArrayCallbacks will be set to disable. And that ArrayCallbacks is a flag that says when the driver gets the data from the camera, does it call the plugins? And by default, that's disabled. And because you can then use it, you can use it so that EPICS is controlling the camera but not doing anything with the data. So you may need to enable that. It's in Save Restore, so you should only have to do it once if you want to leave it that way. Okay, so now we can go to ImageJ, and actually let me stop this. Whoop. So this is the ImageJ main menu. If we go to Plugins, if you've copied this directory that comes with Area Detector into the Plugins folder of your ImageJ installation, then this will appear in the menu. Actually, I should say that the first time you do it, what's distributed with Area Detector are only the .java files, and you need to make from that the .class files. And you can do that by saying right here, compile and run. So that will let you browse to the Java file, you click it, and then it will create the class file for you. But once you've done that, then it'll appear in this menu. So we say EPICS AD Viewer, that opens this window, and it's now saying that the prefix here is 13ps1:image1, which is the prefix for this standard arrays plugin. So I'm giving it the prefix for that standard arrays plugin, and then I say start, and then now this is the image of my briefcase over there, or we could go outside. It's too bright, but I can cut the aperture. Okay. And so ImageJ now here is telling you how many frames a second it's displaying, which is about 19 frames, 18, 19 frames a second. You can zoom that with just the minus key, makes it smaller. Let's do that so we get a little more screen real estate. In fact, by making it smaller, it went up to 30 frames a second. So that was being limited by the CPU power required to draw that display and not by data rates that it's getting over channel access. Okay, so we can go down here and set this to, instead of mono mode, I could set this to RGB1. Okay, so now it's sending from the camera not a monochromatic image, but an RGB image. So that uses 3 times the network bandwidth. So now my frame rate has fallen to something like 10 or 11 frames a second. When ImageJ gets a new type of image, it automatically makes the screen back to some default size, because ImageJ now knows that it's not getting a mono image, it's getting an RGB image, and so it created a new window. I got to shrink that again. So now, unfortunately, this is winter in Chicago. There's not a lot of color out there, but that is a color image, trust me. Here, I could point it at something more colorful, you guys. There's color, yeah. So it does work. But I know that's embarrassing, so I'll put it back. There we Okay. So we're only getting about 12 frames a second. Now what I can do here is, instead of collecting RGB, RGB1 means the camera's putting color across the network 3 times the bandwidth. If I switch this instead to bare, now the frame rate, oh, well, that's interesting. Should have still be up where it was. Yeah, I think the CPU power to display this at full resolution is high. So now we're back to 30 frames a second. So the camera's able to send 30 frames a second. However, if I blow this up, I don't know how well this shows up on the monitor for you guys. You can see that this bare image. It's a little hard to see here because there's not much color, but it doesn't look nice and uniform like the mono image would have looked, because each pixel has a different color filter in front of it, and so the intensity is slightly different from image to image. You wouldn't want to look at this. You wouldn't want to be displaying this, but what you can do now is this bare convert. I can say convert that to RGB1. And let me shrink that again. So now I'm still getting 30 frames a second because I'm sending bare color over the network, but now I'm converting it to RGB on the laptop. And so if you want to do color and your camera supports it, this is a good way to conserve network bandwidth at the price of CPU cycles. But I think, pull up the task manager here, so I'm using about 33% of the CPU, and we could try to figure out where is that. So if I just stop ImageJ, that went down by about half. So half of the CPU was just for ImageJ to display those images. And so it's about, what, 16, 19% now. If I go back to none on this conversion, 10 or 14%. See if it goes back up when I put it back on RGB1. Yeah, so it's using 4 or 5% of the CPU to do that bare conversion in the CPU. But that's definitely worth it if it saves you a factor 3 on your network bandwidth. Now, what it's doing, I mean, it's fairly sophisticated. It's got this pixel had a blue filter in front of it. This one had a green. This had red. This had green. It's taking those pixels and figuring out, if I take the pixel in that upper left, it uses some combination of the intensity of the red, green, and blue in the neighbors to figure out what color to paint that pixel. And then it does that for every pixel. So it looks at the red, green, blue content of the neighbors to figure out what color that pixel is, because it doesn't know what color that pixel is. Its resolution has been degraded by a factor of 4. Its color resolution has been degraded by a factor of 4. And so if you look at the point gray library, there are lots of choices of how you do that bare conversion, which trade off efficiency for accuracy, right? Because you can imagine that to do it very accurately, you've got to do a lot of interpolation, and it's going to be slow. But if you want to do it quickly, you're going to be a little less accurate. And both the point gray and the Prosilica drivers have that capability because it's in the vendor library, but none of the other drivers at present do, because those are the only color cameras I think we've supported. And in mono mode here, see, when I tell the camera to do mono mode, what it's doing, but let me just say that in mono mode, the camera is actually doing interpolation inside the camera to say what is the appropriate grayscale value of this pixel given the different grayscale values of the neighbors, because they have different color filters on them. Typically, the scintillators are quasi-monochromatic, right? They give you more or less one emission energy. But certainly we look at our scintillators with color cameras and you see them in color, but you don't get a lot more information out of it, I don't think, by looking in color. But yeah, one of the things that we're thinking about doing is using them for radiometry, right? We're trying to measure black body temperatures. And typically you do that by running it through some spectrometer and measuring the wavelength. But here you've got you can be measuring 3 colors at once in every pixel. So you can sort of get a temperature map of your system, as long as it's hot enough that it's emitting mostly in the visible and not in the infrared. Although some of these cameras are pretty sensitive in the infrared. If you pull off, they have a filter in there to get rid of the infrared. Okay, so let's just show that we could set a region of interest in the camera. So let's just start reading out at pixel 500 and in X and 600 in Y. And what you notice is that, well, I guess I can use the mouse, is that I've asked for a region size of 1360, but of course it shrunk it down to 860 because you can't start at 500 and read out 1360. There aren't that many pixels. And what I was talking about, so now we're just reading out a sub-image, and now it's up to 40 frames a second, which is being controlled by our exposure time, right? So now it could probably even go faster than 40 frames a second. If I slow this down to 10 millisecond exposure time, yeah, I'm up to 60 frames a second because I'm trying to pump less. I have to read out fewer pixels and pump less data across the network. If I set this region back to 0, what you notice is what I was talking about before. What you might the user might expect is when they set this back to 0, this would pop back to 1360. Right, but it doesn't. It goes smaller automatically, but it doesn't go bigger automatically. So, but if I just hit enter in that field because the BO or the analog output record hadn't changed, I can just reprocess that record and I'm back to where I was. Okay, let's play with binning. I can bin this, say 2 by 2. I'm reading out the whole chip, but now I'm binning it 2 by 2. And first of all, you see that the image is brighter because I've taken the electrons from 4 pixels and combined them into 1 superpixel. So I've got a more intense image. And also now my frame rate is up to 53 frames a second. So, I mean, here it's only an 8-bit camera. So I don't think that doing this will increase the dynamic range. No. And some cameras, it actually, when it combines that charge, it combines the charge in the vertical direction on the CCD, I believe. Then it comes down and it combines the charge in the X direction in the shift register at the bottom of the CCD. And so that means that the shift register here has to have an electron capacity that's 4 times the individual pixels. And sometimes they don't. Or if I binned it 8 by 8, I may saturate when I wouldn't have otherwise, because I'm running out of electron capacity in some shift register. The binning works fine for, so let's go for mono, but it doesn't work for color. You notice this image is not the right color. It was kind of yellowy orange before, and now it's pink. And the reason is, you've mixed colors. If you bin a color camera this way, you've just mixed all the wrong colors together. So you really can't do this. If you want to bin a color camera, you need to do it later. You can do it in the ROI plugin, but you can't do it on the chip. And the same is true if you use Bayer and then do the conversion on the host, you get the same problem because you've mixed the information before you read it out. So now, well, you've seen the exposure time. This is 10 milliseconds. Here's 20 milliseconds. Obviously, it's brighter. Down here is the gain. Right now, it's at a minimum. If I turn it up to 5, this is just increasing the electron multiplication, the electron gain in the amplifier in the camera. So now we're in continuous free run. If we go instead to fixed rate, now you see the frame rate is 20 frames a second, which is determined by this acquire period. If I make that 0.1, it's now going to be 10 frames a second. Because it's in fixed rate, it uses this number. It tries to go this fast. If you set this too small, like I'm asking for 100 frames, got to type right. If I ask for 100 frames a second, I'm not going to get it. You notice I asked for 100. It left it at 0.1 because the driver tried to ask their software for 100, and it returned an error. So that's outside the range I'm allowed to ask for, so it didn't even change it. It's giving me an accurate readback of what it's really doing. Let me try 04. Yeah, so it allows me to do 40 milliseconds, which is 25 frames a second, and it's capable. It is doing that. Okay, and it probably can do 50 frames. It's unbinned. It can't do 50. It can do only 30 frames a second. Anything else here? So you saw this image counter. I mean, I can reset that, so it goes back. Okay, so we have the modes here are in this camera are single, multiple, and continuous. So single means every time I press start, it just collects one image. Multiple means it collects this number of images, in this case 10. So it collects 10 images and then stops. Some cameras have, the Pilatus is one, and there are a number of others, have the ability to do, the terminology there is usually accumulations. So it can accumulate onto the chip. So it can basically take an exposure, but not read it out, and then take another exposure and keep adding them up. And then only after you've done 50 of those to read it out. That would be used often for some time-resolved work where you're running at kilohertz rates, but you don't need the images. It takes many repetitions to get a useful image. And so detectors that support that, we usually call that accumulations. Okay, so this screen takes you to something that's sort of like a more screen for the Prosilica, where you can control. These are output signals that can come out of the camera. You have to build a breakout box, that you can have these 2 output signals or 3 output signals. You can define delays. You say, when I give you this signal, wait 10 microseconds and then take an image or something like that. This gives some information on the GigE itself. It says driver type filter. In that case, what I'm doing is Prosilica gave me, has a driver that they install on Windows, which filters the GigE packets. And so only if it's a packet from a Prosilica camera, it goes straight to their driver. It doesn't go through the Windows network stack, the Windows TCP stack. And so it saves CPU time, because it doesn't. But if you look at your network usage, like in fact right now, the camera, let's go back to continuous and start. So now we're getting 25 frames a second at 1.3 megabytes or something. That's quite a bit of network bandwidth. But if I go to networking here, it tells me that my local area connection is using 0. So these frames are being taken off before Windows ever sees them. So it doesn't know what your network utilization really is. It reduces the CPU time. It doesn't really make the camera perform any better unless you're starved for CPU cycles. Okay, let's go look at some plugins. So you saw we're using one plugin right now to put the images out as Epic's waveform records. We could enable here an ROI. So this is the first region of interest, and let's, so we could use it to make the images smaller, say 500 by 600. And now if we take the standard arrays plugin, which is currently getting its data directly from the camera, which is PS1, and change that instead to ROI1, now we're seeing, just a sub-image. The detector's still collecting the full image, but the ROI has restricted us to a sub-image. And in the ROI plugin, you can change reverse it, say, in the X direction. So now the image is flipped that way. We could also go back. There's an auto size. Yes means, so this will make it so that anytime the input image changes size, that dimension of the region of interest will also change its size to match. Here we could do binning. Okay, so now you notice that when I binned, so the binning in the ROI plugin is just a sum, and these pixels have overflowed. So now we've gone to a saturated image. We could get rid of that by saying, if we scale the result by dividing it by 4, we should be back to an image that's not saturated. So I enabled the scaling and set my scale divisor to 4, and I'm back to an unsaturated image. We've got, so if I disable this guy, now ImageJ is saying frames per second 0 because it's getting, the standard arrays plugin is getting its data from this plugin, which is now disabled. I could say callbacks block yes. And right now we're getting 25 frames a second. It doesn't actually, it doesn't have a visible effect. But this is now not running this plugin in its own thread. It's running the plugin in the driver thread. So in a sense, it's slowing down the driver, but not enough so that we're losing frame rate. Let's go to the statistics plugin and enable this. And if we compute the centroid, and the profiles and the histogram, let me go to free run. So now I'm at 30 frames a second. Now this isn't being stressed enough at this rate to be dropping frames. Right, we could try that, because that'll suck up, that's right, that'll suck up some CPU. So go find that. Set this back to PS1. So that's now live. Yep. No, it's still not dropping any frames. Let's just see what my CPU utilization is. Yeah, there's no core that's saturating here. But if I ran this with the simulation detector, we could get to the point where this plugin would begin to drop frames. The queue size, the number of free elements in the queue would go down to 0, and the number of dropped arrays would go up. What I was going to say is that if at that point you stop the detector Or I think even if you disable the plugin, it will empty the queue. And if that queue's got 2,000 elements in it, it could take a while. You know, if it's writing a file, and you know, it could take a while to write all that stuff. Okay, so we've seen the region of interest, the statistics. Let's go to a file plugin. So here's a netcdf file plugin. It's writing to C data. It tells you up here, does that directory exist? So you get, you know, at least some feedback as to whether you've made a typo here. But in the next release, there'll be, you know, a way here to specify that you should create the directory if it doesn't exist. The name of the file, the next file number, auto increment, the format, and right now it's in single mode. So I need to enable it. So now you see it is getting callbacks. It tells me about the data. So now if I say save, it says the last file name here is cdata testnet cdf 006, 007, 008. And the way this works now, and which is what I'm saying I think needs improvement, if you wanted to save a whole bunch of images single here, you would turn on AutoSave. And now it's saving, you know, files 80, 90, 100, blah, blah, blah. If you wanted to save into and that wrote a whole bunch of files, each of which only had one frame in it. If you want to save 100 frames, put number of capture to 100 and do it in, let's say, capture mode, then you do start. And now it's capturing into RAM. It's not writing to a disk file at this point. And in fact, it still hasn't written to a disk file. In capture mode here, you either have to press save or have set AutoSave to yes. So now if I do save, it's writing out those 100 frames. If I do instead stream and start, now it's actually writing the file in real time as those frames come in, and you don't have to press save, and you don't have to press autosave. As soon as you do start, there's only one option here, which is to start to write the file to disk. And as I said, I think we'll get rid of this concept, single stream capture. We'll have the number that you want to save and the number you want to save per file, and get rid of autosave here as well, so that you have to press effectively this button to begin saving files, and you have to have specified some finite number of files to save so that you don't accidentally fill up your whole disk. Okay, here's the transform plugin. So now we want to tell the standard arrays to get its data from the transform plugin. TRANS 1. That's not updating because the transform plugin is not enabled. So we enable that. Okay, so now this is a live image, and right now the transform is none. We could rotate 90 degrees, rotate 180 degrees, 270, a simple mirror, which is an X. And then there's combinations of mirrors with those three rotations. So a mirror plus a 90-degree rotation, mirror plus 180, so on. And if we look, this plugin is also, keeping up. It's not dropping any frames, doing these geometric transformations. Let's go to the process plugin. Okay, so we want to enable this plugin, tell the standard arrays to get its data from the process plugin. So now this should be live. Yep. Okay, so now we could say, take the current frame and make that be a background frame. So now we're going to call this, no image, or background. And now if we do, oh God, I should have done it when somebody was walking by. That would have been good. So now if we enable background subtraction, so now this is just displaying the difference between this frame and that background that we captured. And this is probably, rolling around to negative numbers. This is an 8-bit data stream. So what we probably want to do here is to tell it to output this image, let's say, as a 32-bit float. But no, the problem is that works, except that we're transporting the data across a waveform record, which is only 8 bits. So I can convert it to 32-bit here, but unless my waveform record has a bigger data type, it's going to be limited by what we see here. I might be able to make that, however, be int 8. Does that help? No. So instead of unsigned, to make it a signed integer. No, I guess it doesn't. But anyway, you can see what's going on here. So we could do background subtraction, could do flat field normalization, scale and offset. So let's do instead here an average. So we could do, what happens if we make a pretty short exposure time, like 1 millisecond. So now it's so what we want to do here is figure out, okay, what is the range of the data that we're getting at this point? So if we look at the statistics plugin, it's saying that the mean number of counts in this image is 11 counts. So at 1 millisecond, it's mostly pretty dark. There's one, some pixel that's up around 180. Well, maybe that's where we're over here looking at the light. Yeah. So now the maximum is also 11, and the minimum is 2, and the mean is 6. So it's a pretty dark image at this point. So in the processing plugin here, if we enable scale and offset, and let's say we scale it, so it said the average counts was around, well, the maximum counts was around 11, so if we scale it by 25, so now we've got an image that's, sort of filling the grayscale of 0 to 255, but it's pretty noisy, right? We don't have very good statistics in that image. But if we now say that we want to enable a recursive filter of 30 frames, and I want to output it on every array, and let's not automatically reset it, so it'll just be constantly filtering, we've now got a less noisy image compared to disabling this. We could do a true average and only output, when we've when we've gotten 30 frames. So that's going to be about once a second, right? It'll put out an averaged image. Right. So, you know, there are a lot of people, I think, who can use this capability when they're trying to read, you know, low intensity images and they want to average a bunch of them together. And, you know, you can't because, well, for instance, on the Perkin-Elmer, I think the maximum exposure time on the Perkin-Elmer detector is 5 seconds. And if you've got a weak signal, you may want to average, you know, add together for a minute before you bother to save the data. Now let's see, is this doing anything with dropping arrays? No. You know, even doing this recursive filter, it's not having trouble keeping up at 28 frames a second here. Okay, let me do one more. We're getting, timing is pretty good. Let me do the overlay plugin. So I'll tell this to get its data from over 1. And obviously you can be chaining these together. I've been switching the standard arrays from this plugin to this plugin to this plugin, but you know, I could have been looking at the process plugin, which then sent its data to the overlay plugin, and then I get the data from the overlay plugin. So we go to the overlay plugin, which is here. Oh, and we enable that. Now we want to set our exposure time, back to something more reasonable. Okay. So there's the image. Okay, so here's the overlay plugin. So I can pull up, there's a screen here that combines 8 overlays on one screen. The overlay plugin itself is enabled at this point, but each of the individual overlay features is disabled. So if I enable the first one, so it's set to display its name, which is just for, you know, user friendliness, is ROI1. It is getting its data from the first region of interest. So that region of interest doesn't have to be processing, it just has to be defined. So let me go define that first region of interest to be something other than the full chip. All right, so now this is showing us the position and size of the first region of interest as an overlay on this screen. And it was in mono mode, which is what I'm in right now. It uses, for the intensity, the green value. So it was set to 1. So if I set it to 255, that'll be white. I can say that, so that's with the shape being a rectangle. I can also make it a cross, which is at the origin of that, or the upper left of that rectangle. We can also make it be text. So I could say, you know, hello world, and make the shape be text. And now there's hello world up here, and can change within pretty limited ranges the font that's used for that text, and also it's putting the timestamp from the array in here, and you can control with this time format how it displays that timestamp. I typed world wrong. Gotta fix that. Oh. Let me see if there's any other things. So even though this is a link, I believe I can change it. Yeah, I moved it. It will only change it to this link value on a callback from that link PV. So if this were changing, then this would be updating to reflect this. But it only got the callback once when it opened, probably when the last time this changed, it got a callback. But now I could manually change it as well, just by typing a number in that field. So I can move the overlay around. So this is often pretty useful. You can mark where the beam is on your sample, or as I say, where the regions of interest are, that kind of thing. It's fairly simple. It's not fancy graphic overlays, but enough to do what we need to do a lot of the time. Anything else that we wanted to do? Yeah, one thing that's on here, this is basically something sort of straight out of Synapse, is that there's for every IOC now, there's a sequence or a string, an sseq record loaded. Which is useful because now if you have a sequence of operations that you want to do, you could put them in here. Put in a PV name that's like, open the shutter, or move the sample, take an image, move the sample out, take another image, whatever. Some sequence of operations that you want to do, you can put in here, and you can say whether for each step, you want to wait for completion or do a whole bunch of operations and then wait for all of them to complete, or whatever. It's just all the stuff you can do with the sequence record. There's nothing area detector about it, but it's a convenient thing to have in the crate, that the user can configure a set of steps that they then just push one button and it does a whole set of steps, including stuff with the detector, but not limited to the detector, any Epix PV.